So here we're going to be talking about conduction resistance for radial systems. If you recall, for planar systems, we talked about a conduction resistance So let's just remind ourselves. We said that Q is equal to minus K dt dx for a planar system, and that this can be thought of as K delta T over L. We said that this can be put into resistance form as delta T over R, where this resistance, R, is equal to L over K. So this is a conduction resistance in this one-dimensional planar sense. We want to do the same kind of analysis for radial systems. And so these radial systems are either cylindrical systems, as you might see in pipes and tubes, or for spherical shells. All right, so we're going to first talk about cylindrical shells, and I said that these cylindrical shells could be pipes and tubes. So we're really focusing on pipes and tubes as our system. And so to make this perhaps more practical, imagine that you have, and this is what we're looking at here, you have some sort of tube where we've imposed some temperature T1 on the inside and T2 on the outside. So inner temperature T1, outer temperature T2. We're interested in understanding what the heat transfer rate is for this tube. And we're going to talk about the heat transfer rate in this particular section either as Q prime, which will be watts per meter, so the heat transfer per unit length of the pipe, or simply in terms of Q dot, which will be the total amount of heat that's transferred through this pipe. And that's, again, over the overall length of the pipe. We'll certainly use Fourier's law and an energy balance, but just to think about this energy balance a little bit, let's imagine a situation where, again, for some length of pipe, we understand that we have 100 watts that's being dissipated through that pipe from the inside. So we have put some sort of resistive heater inside this fluid and caused the fluid to transfer 100 watts to the inside layer of the pipe. Well, the fact is that since there are no transients, so it's steady state, so if we make a temperature measurement anywhere in that pipe, we get the same temperature, and there's no generation or sink inside that pipe wall, that we have to have 100 watts to come out at any given radial dimension. So it says that the heat transfer rate at any R location is equal to the heat transfer rate at some R plus delta R, differentially thin layer, or even a macro, large layer. All right, now we ask ourselves, we say, okay, well, let's understand what Fourier's law says. Well, Fourier's law says that this this is not Fourier's law specifically, but the heat transfer rate is equal to the area times the heat flux, double prime, which is equal to this area, which is the perimeter, times the length, so this is the pipe length, times a description of the heat flux. And so this description of the heat flux is where we invoke Fourier's law. So the heat, this is just saying the amount of heat that's transferred, Q dot, is equal to an area description times a temperature gradient. But we don't know what that temperature gradient is at this point. We just know that that's the case. And so when we when we sort of reformulate this, we can say, hey, you know, dividing through by this 2 pi kl, so 2 pi kl, we have that q dot over 2 pi kl is equal to minus r dt dr. And we said earlier that q dot is a constant, that no matter where we are at any radius within this pipe, that q dot is the same value. So we know that this minus r dt dr is a constant. We're going to call that constant C1. We call that constant C1, and we pull the r to the other side. So we're simply taking that, we're going to divide both sides by this constant r. So we have a relationship between dt dr and this constant. What you're going to see is that we're going to find out what the temperature variation is with the radius, we'll have to integrate this relationship. So this is where we left off. We said dt dr is equal to minus C1 over R. We can integrate this. We understand that the integration of anything over R is just going to be this log R. So we really had that dt is equal to minus C1 over R dr. We integrate both sides. And the relationship is the integral of dt is t. The integral of dr over r is ln r. And we have a constant of integration C2. We apply these boundary conditions. So remember, we need boundary conditions to close this system. We know that at r is equal to R1, that is the inner radius of this pipe. The temperature is called T1. And at the outer radius, the temperature is defined to be T2. Understanding what these boundary conditions are will allow us to figure out what these two constants are, C1 and C2. The simplest way to do that is that we substitute T1 and T2 into this relationship for the temperature that we just integrated, and we simply subtract, because by subtracting we get rid of the C2s. The C2s are going to cancel out. We get the T1 minus T2 is equal to this relationship in terms of ln R1 and R2. We understand that for example, that log A minus log B is equal to log A over B. So we use that relationship for R2 and R1 to identify what C1 is. So basically solving for C1, we see the C1 is delta T over ln R2 minus over R1. We can solve for C2 pretty easily now because we already know what C1 is. So the same type of, we could solve this in terms of T2 or in terms of T1, and we chose T1 here. And so just think about it this way. In both cases, we know what this relationship is, and we would have had, for example, this as T2 plus T1 minus T2 ln R2 over R1 ln R2 if we had solved it in terms of T2. So we solve for this constant C2, and we can sort of rearrange this relationship because all we're doing is we're substituting our T1 plus this other stuff into our formal equation for T, and we arrive at a relationship of delta T over the driving temperature difference in the whole problem in terms of this log ratio. And let me just revisit that because I don't know if that was sufficiently clear what I said there. So remember that we have this relationship for T. We said that T is equal to minus C1, which is T1 minus T2 over ln R2 over R1 plus C2. Okay, this is from what we had. I'm sorry, there's a LNR here. Okay, so this is what we had before. And all I'm saying is that here I chose T1, so I substituted T1 here. I said, this is T1 is equal to minus T1 minus T2 over ln R2 R1 ln R1 plus C2. But just as easily, I could have said T2 is equal to minus T1 minus T2 over ln R2 over R1 ln, but now I have to be consistent, R2 plus C2. So these are equivalent. This is all the same stuff, okay? And all we're saying here is that we just do a little bit of rearranging on this because, let's just make sure that this is clear to you guys, that what we're saying here is that T is equal to, so we're going to just rewrite this, ln R plus C2, which is T1 plus T1 minus T2 over ln R2 over R1 ln R1. So subtract off T1 from both sides. T minus T1 is equal to, and I think that you see it here, I can look at this minus T1 minus T2, okay, times, and what I have left is I have ln R over ln R2 over R1 minus ln R1 over ln R2 over R1, close bracket. So I've got to erase this. And so we basically just dividing, we stick this guy over here, so we put that in the denominator. That's where we get this. And what we have left is ln R1 minus ln R. So this is where we're getting these guys. And actually, you see, I changed signs on us. So I took this minus sign over here, so that's T1 minus T. And so I get ln R minus ln R1. This is ln R over R1 over ln R2 plus R1. So check this. Make sure that you understand this. So verify. All right. So the long and short of it is that it gives us what Q dot is in terms of those constants. So let's understand that again by referring back to what we had before. So we said that, if you recall, we said that Q dot over 2 pi KL is equal to a constant. Remember, we call that constant C1. Well, we know what C1 is. We've solved for C1 in the last version of this, and we said that that C1 variable is, in fact, what we've defined here as T1 minus T2 over ln R2 over R1. So by virtue of that, it gives us this recipe to say what Q is in terms of these different variables. So this is from the last screen. So given this, we arrive at the definition of Q dot by simply multiplying 2 pi KL by this parameter. If we always think about the resistance in conduction problems as the potential, the driver over R, we quickly see that the resistance for these cylindrical systems is ln R2 over R1 over 2 pi KL. So this is the result that we want to hold on to. All right, so that's the cylindrical system. And let's take a break with that.